Thank you. So Apple SMC is the place to be. Why is that? So this talk is basically going to be a part 2 of a talk I gave last year at REcon in Paris. We'll talk about what the SMC is. And back when I gave my talk a year ago, it was covering the SMC on older Mac laptops, which are now pretty much getting defaced. So this talk will update pretty much all the research that was done for the new SMC, show you why that's relevant, what the SMC is and what it does, and also actually flash some stuff on the SMC. Last year's talk was only more of a theory. Here we're actually going to do some practice and flash some custom code if things work well, if the demo gods are with us today. So brief bio about myself. I'm a Windows kernel guy, but every once in a while I have these like bipolar moments where I go back to my Mac side. So I'm not going to do a Windows talk for once, or for twice, I guess. But most of my background has been doing Windows kernel research since about 1999. So I was the lead kernel developer for ReactOS, where I worked on a lot of the kernel code for that project, which is basically an open source implementation of Windows. And I also worked on the Windows internals books, 5th edition and 6th edition. And I do a lot of trainings like here at REcon about Windows. So it's good to take a little break from Windows from time to time. So what is the SMC? Well, it's a chip in your Mac, tiny little microcontroller. Anyone can flash it if they know how. It doesn't have any code signing on it. But you can't actually read the code that's on it. So anyone can write to this chip, but you can't actually see what someone might have written inside of it. And this chip manages things like your light sensor, nothing much. Also protects your disk. If you were to drop your Mac with a rotational drive, it'll actually lock automatically so the heads don't move during impact. On an SSD, it doesn't matter so much, but on a rotational disk, that's obviously something important. So SMC handles that. SMC also stores your file vault key, so that when you actually set up your Mac to automatically resume and not ask you for your password because you're lazy, well, it has to be stored somewhere. So the SMC is going to store that password temporarily while you're suspended and coming back from suspension. It also has something called a Ninja timer. A little demo of the Ninja timer, see what that can do. And it can talk to almost any peripheral on your Mac. It can talk across USB, LPC, which is the local pin count bus that talks to your DMA controller and your interrupt controller. It can talk over ACPI. It can send messages to ACPI, receive messages from ACPI. It can talk to PCI, which is Intel's performance and power bus. And it even runs when your computer's turned off. So if you can turn off your Mac, completely power it off, not just hibernate or suspend, turn off all the power, it'll still run. It has its own power draw from the battery, which is, as you'll see, fairly low, and it will still run code even when your Mac is actually completely powered off. And it can communicate with the kernel. There's a driver in OS X and even Linux that communicates with the SMC. So it talks out to the actual host OS as well. And it's also responsible for small little things like managing current, voltage, and talking to the battery. So you can see, well, this would be a pretty interesting place to put some code in a place that anyone can flash, that no one can read, that has access to pretty much everything on your peripheral, and that runs when your machine is off. So what exactly is the SMC? Well, it's a little chip. And the thing you see highlighted here in yellow is your Intel processor. And next to it, highlighted in black, which is kind of hard to see. Oh, there goes the zoom. Well, this little chip right next to it, that is the SMC on the modern Mac computers. So these days, instead of being an old 8-bit Renaissance microcontroller, it's actually a 32-bit ARM Cortex M4 processor running at 80 megahertz. So it's actually faster than computers like 15 years ago. So it's a normal ARM Cortex chip, 32-bit, 256K of flash ROM, 32K of RAM, and EEPROM. And it can draw as little as 1.5 microamperes when it's running. So if you turn off your laptop and your battery's at 1%, this thing can probably still run for a few days, if not a month. It has timers, it has watchdogs, it has access to the PS2 port, like I mentioned, bus access to SM bus, LPC, ACPI, everything but PCI pretty much. But over LPC, you can do DMA, and you can probably reach out that way as well. So it's really a well-connected processor. Now, this new model is from TI, Texas Instruments, and it's called the Stellaris. And I like there's a single public white paper on it that says this chip provides complete system control, and it has prolific connectivity. I thought that sounds like a really good chip to run some code on. So they really market it as this chip can access everything you could dream of. So that's just a little basic, just for reference when you'll have the slides, kind of what it looks like, all the buses that it has, analog digital converter, JTAG. Basically, it's a full-blown processor. Your smartphone a few years ago basically had a chip like this in it. So to actually compile code against this, you can use GCC. It's a standard ARM Cortex M4 core, so you just target the M4, and you can build on this. TI even has a free evaluation kit and an SDK they call the Launchpad. And it's actually only $12. So you can go to TI's website and get the physical board that has not exactly the SMC chip, but a very similar one. Basically same processor, same memory map, and you can use that to basically play around, write some code, etc. Now, I want to stress that Macs are not the only computers that have this chip. Many Intel reference platforms use the exact same chip. They don't call it an SMC on Windows computers. They call it an ACPI EC, an embedded controller. So the ACPI EC on your Dell, on your Toshiba, on your Samsung is also probably this chip or a very similar chip. There's about 3 main chips that are used for providing this kind of functionality. In fact, Google Chromebook actually uses this exact same chip if you buy the Google Pixel, so the one they actually make. Not the Samsung, which is a different one, but the Pixel uses exactly this chip. And the white paper and the data sheets for the chip are not public, but Google actually open sourced their firmware because almost everything on a Chromebook is open source. So you can see their ROM for their ACPI EC. And that was really helpful in terms of seeing some of the variables, the registers that are not documented anywhere. So thank you, Google, for documenting that. Probably violating your NDA, but thank you. So officially, this is now called the Tiva processor, not Stellaris. It was also called Blizzard before. So if you Google for Blizzard, Tiva, or Stellaris, it's probably the same chip. So like I mentioned, you can get an eval board for about $13, and then you can start coding with it. IDA, of course, perfectly supports the ARM Cortex M4. So you can get an Apple SMC file, and we'll see how to do that. Load it up in IDA, set the right ROM base, set the right RAM base, and then you can pretty much start reverse engineering the code. And since Hexarray supports ARM, you can actually now read this in C code, which is a lot better than reading Renesas ASH4 code like 2 years ago. So it's much more readable in terms of understanding how it works. So I won't bore you with the details, but basically a Cortex M4 is kind of like a standard ARM processor, except it's less complicated. It's got less execution modes, it's got less instructions, and it's a lot simpler than a full-blown ARM processor. So these are meant for as microcontrollers for things like embedded robots and things like that. They're not meant as fully blown application processors because that would be overkill. But you still have access to an FPU. You have access to over 200 instructions. You have your 16 registers. So it's a very powerful platform for actually writing code on it. As I mentioned, your smartphone a few years ago probably ran something like this. Now, the thing that's really interesting about a TI is that outside of the flash ROM, where you can flash your own code, there actually is a TI ROM that they put in. So there's a mask ROM. And this mask ROM has an API library for accessing various kinds of peripherals. So instead of writing your own code to reach out, you can actually call TI's code. And this is a really poor choice of callers, but let's see, it's a little more readable this way. Basically, you've got a table for like the watchdog, the interrupt, the USB, DMA. It even has a CAN bus, so sometimes you'll even find this thing on a car. The accent EEPROM, accent the fans. So what's really nice is that instead of reverse engineering what bizarre I/O ports are being accessed by Apple's SMC code, you literally see the API calls that are being made to this library, because a lot of the SMC code is actually using this API library. And this library basically starts at address 100,000. And all you have to do in IDA is define a segment starting 100,000, put the right types, because it's all documented by TI in their rom.h file, and then you'll be able to see the code calling these APIs in the ROM, which makes it a lot more readable. And if we have time, I'll show you some IDA dumps on how that actually looks like. So how does Mac normally talk to this thing? Well, it has 2 access modes. Now, the traditional Renesas chip had an LPC-based I/O port access. So you basically had port 300 all the way to 301F, and that's how you talk to the device. 304 was your command port, and 300 was your data port. So if you're familiar with serial programming or VJ programming, the same idea, you in and out some bytes, and you have an error register as well. And that's how the Linux driver still does it. That's how most tools today are still going to access the SMC. Now, with the new chip, Apple actually added memory mapped mode as well, which is a lot faster in terms of performance. And so you also have the chip memory mapped at FEF0000000. Regardless of what access mode you have, it basically has a few simple commands: read a key and write a key. And we'll see what exactly a key is. Get a key by index. So if you know the index of a key, you can also get it that way instead of getting it by string. Get key info. And with that, you can dump all the keys. So you can dump information about a key, get a key, dump all the keys, read a key, write a key, or you can also reset the chip. So those are things that you can do when the chip is normally in application mode. So what is application mode? Well, the chip, actually, the way Apple implemented it, has 3 separate execution modes. So out of that 256 kilobyte flash ROM, there's actually 3 separate pieces of code on it. The first piece of code is called boot mode. And boot mode is kind of the guaranteed, we should never flash this. This is our basic execution mode. The boot mode is able to flash things. So while in boot mode, you can flash the update flasher. The update flasher runs in update mode. And in update mode, this is how you normally update the actual code on the SMC, which is called application mode. So boot mode protects and flashes update mode, and update mode protects and flashes app mode. And the idea is if you flash complete garbage on a chip, you still have update mode to flash correct stuff. If you flash a garbage updater, you still have boot mode to actually flash a correct updater. And if you flash garbage all over the chip, well, then your machine is dead. So when you're in application mode, you have those previous commands to read keys and write keys. When you're in any of the boot modes or update modes, you actually can flash the processor. So you've got 3 commands to flash a region of memory, to authorize flashing, and to slat the flash time. And authorized flashing sounded kind of interesting, like, ooh, right, the chip has AES. They probably use signing now. No, authorized flashing just means I'm about to flash you this address for this many bytes. Can I? And the chip just says, yes, you can. So it doesn't really authorize anything except telling you, go ahead and do it. So how does it look like in terms of flashing this thing? Well, in terms of the LM4F, the actual processor from TI, you've got that first 256K region, which is your flash ROM. And then you've got a vast nothingness till you reach 100,000. What you've got at, 1 million. At 1 million, you have the TI ROM. And that's where you have things like the peripheral driver library that I talked about that code can use to actually access USB, to access PCI. So that's kind of like TI's operating system. They also have their own micro USB serial bootloader there. So theoretically, if you completely destroy your SMC, you can still, if you have the right hardware, connect to a serial port, to the TI ROM, and reflash the SMC from the beginning. Although the many times that I bricked various different Macs, the Apple Store people are like, no, this is dead. You need a new motherboard. It's like, no, you can connect to the TI ROM. No, it's dead. I don't know what you're talking about. So I don't know if they actually know about this. 20 million, you've got your RAM. So that's your 8 kilobytes. And the RAM on this chip is kind of interesting. It's actually aliased through what's called, bit binding, I think. And the idea is that you can do atomic operations because you've got RAM mapped across two different locations. And then at 40 million, you've got your peripheral registers. So that's where you can access USB, PCI, PCI, LPC, the AD controllers, the fan controllers, and the GPIO controllers, everything else that's plugged into the chip. And your code can actually either access these registers or you can use the library that TI provides. In Apple's case, they seem to do a little bit of both. So some code directly talks to peripheral registers, and then you have to use a data sheet to find out what register is what. Other code uses the API library, and then it's a lot easier. So you can just read what the API call actually is. So you've got a bunch of peripheral registers at 40 million. You've got a few more at E000, and that's pretty much it. So you've got a 32-bit address space, but really you've only got 8K of RAM, and you've really only got 256K flash ROM. The rest is pretty much just peripherals. Now, out of that flash ROM area, the way that Apple sets it up is you basically have your reset vectors at the beginning. So that's a 2 kilobyte region where the chip actually boots up. And there's a magic value at the end of that region. We'll get back to that magic value. Then you've got the bootloader, which is the basic updater, which is 20 kilobytes, and then it has a magic value at the end. Then you have the update loader, which is 20 kilobytes, and a magic value at the end. Then you have what's called the EPM, UV, and CV area. And I'm still trying to find out exactly what these things are, but they seem to be related to essentially managing voltage on the processor on the motherboard. So they seem to be like what actually control the power guidelines on the processor. And then you've got your application region, which is where the actual SMC code lives, which is 210 kilobytes. So add that up together, 210 plus 2 plus 2 plus 20 plus 20 plus 2 gives you 256 kilobytes. And it also has its own magic. And we'll get back to what exactly these magics are. So how does the code actually boot up? Well, so you've got your ROM, the actual application code, that starts at B80000 at the region based on a previous slide. And this is often called the user mat. If you look at some of the documentation, some of the strings, you'll see referred as a user mat, because in the Renaissance chip, in the old chip in 2011 earlier, this is what Renaissance called it. So there's a reset vector at offset 4. So offset 4 in this previous address map, that's where you've got a reset vector, and that's a branch instruction, which on the firmware jumps to address 250. So address 250 is still in that reset vector area. Address 350 will then call another function at 362, which is actually your main. The main will then compute a magic value associated with the update loader. And if the magic value that it computed matches the magic value that's stored in the actual ROM, then it's going to boot the updater at 5805, so offset 5 in the updater. And then the updater will eventually boot up the application code. If the updater is damaged, in other words, if the magic does not correspond to the value that's expected, it's going to compute the boot updater magic instead. And if that's valid, it's going to boot in the boot updater, and the boot updater will then let you update the update flasher. If the boot updater is also screwed up, then you're hosed. The chip just basically goes in an infinite loop, and then you don't have a working computer anymore. So what does the actual ROM code do once it gets booted up? Basically, it does a few things, mainly listening to interrupts. Interrupts coming from the various devices on your computer, such as power, thermal interrupts on a processor, saying the processor is getting too hot, thermal information from the fans, ambient light source information if your laptop has an ambient light source. The OS can also send it messages. Various ACPI events can send a message. So it basically just looks at what is going on in your system based on the various sensors that are there. It uses the accelerometer and the gyroscope as well to see if your laptop is falling down, so it can lock the drives. And it listens to notifications that can come in as well. It can also generate its own interrupts. So it can receive interrupts, and it can generate interrupts on the bus, and these interrupts are then captured by the driver that runs in the OS, and the driver will then take action based on those interrupts. So for example, when the SMC chip senses that there's a drop because the accelerometer sends it the information that is a sudden change in G-forces, it'll send an interrupt to the OS driver, which will then talk to the SATA driver or the HCI driver to spin off your disk so that it won't get damaged by the time it falls down. So they've got a two-way communication between the two. So we mentioned earlier that there's these keys that you can read and write to. The keys are the primary way, other than the interrupts, through which the OS interacts with the SMC, and the SMC interacts with the OS. So the keys are basically 4-character byte tags, so ASCII usually, and they describe some sort of functionality. Now the SMC firmware has a handler for each tag, for each key. So you send it key 1, 2, 3, 4, and it's going to do something when it receives that key. You've got a special key called number of SMCs, and that tells you how many SMCs there are. And you've got a special key called number keys, hash keys, and that tells you how many keys there are. So you can actually dump the keys by asking the SMC what the keys are, and then you can enumerate the keys. But we'll see that this information comes from a key table, but that key table doesn't accurately represent all of the keys, because they know that you can dump the key table. So opening it up in IDA, this is essentially what a key table looks like. These are the key tags. So you've essentially got some 4-character tag in there. And then you've got some attributes that we're going to see in the next slide. Then you've got the actual size that's expected associated with this key. And then you've even got the type of the key. And next to that, you've either got a function, which is going to handle access to this key, if it's something complicated that needs an actual function, or if this key is just a variable that can be set or written, you'll just have a variable. So in some cases, you'll note that my IDB says there's a function like SMC get locks or SMC handle ACCL. In other cases, just G underscore ACIN, because that's just a variable. So quick example of what the SMC is useful for. When I have my power adapter plugged in, if I send a key read command to ACIN, I'm going to get this variable back, which is ACN. Basically, do you have AC current in? So that's a read-only value that I can read without calling any function. But if I want to get the adapter ID to see if I'm using a copied Chinese power adapter that did not cost $140, well, that has to compute the actual AC adapter ID. So if I send it ACID, it's going to call this function that I've called handle ACID. And that's actually some ARM assembly code that's going to run, talk across the I2C bus where my AC charger is plugged in, and figure out what the AC charger's identification bytes are, and then determine if this is an authentic Apple charger or not an authentic Apple charger, and warn you that the charger is not supported. So in some cases, we count functions. In other cases, we just have direct variables in there. So what are those attributes? Well, basically, a key can be defined as read, as write. It can be defined as either a variable or a function. So either I need to call a function or I can just read a variable. It can be defined as a const. So basically something that can be modified once, but not only after that. Or it can be marked as private, and we'll see what a private key is. And it can also be marked as atomic, but I'm not sure what exactly atomic means in this context. But these are basically different attribute flags associated with the keys. So the key table, therefore, describes the access control mechanism. So if a key says that it's read-only, you can't write to it. If it says that it's writable, you can write to it. If it's a function, basically what happens is that in R1, you get either code 10 or code 11. Code 10, which is read, code 11, which is write. And then the function can implement its own access control. So it might say, well, you're sending me code 11, which is write, but I don't want to let you write. And the input buffer from the user, which is also the output buffer, comes in R0. So they always basically have two parameters. And we'll do a few demos, and I'll show you a few key examples of this. Now, a few years ago, some Apple service technician in Belgium basically leaked an internal Apple document that had a list of the keys. And these were the keys on an old Mac Pro. And this is how Linux and most other OSs are able to get things like the temperature, the fan speeds, monitor the battery, because without these keys on a Mac, you have no idea how much power the battery has. You have no idea how to program the fans. And basically, obviously, it's useful for Linux to know this kind of information. So these keys are really useful to figure that out. The keys also, if you look at them, reveal a lot of interesting information, like the fact that there's a ninja action timer. Ninja action timer lets you be a ninja and either shut down the computer after X seconds or reboot the computer after X seconds. And I'll do a little demo where I'm actually going to set up the ninja action timer to expire in like 15 seconds or 10 seconds. I'll power off the computer, and you'll see it'll turn off on its own. This is actually used by a watchdog. So if there's a driver on the Mac that basically reprograms the ninja timer every 30 seconds, and the action is reboot. So if it doesn't get reprogrammed every 30 seconds, it's like a dead man switch, and your Mac will spontaneously reboot. So if it freezes and just runs at maximum CPU and nothing is happening, the driver stops running, the ninja timer will count down to 0, and then the ninja action will happen, which is basically the reboot. So it's got a lot of keys here to manage basically thermals, fans, and I'll do an example of how those work as well. Now, there's some more interesting keys in there, two of them which are widely known by the Hackintosh community, which are OSK0 and OSK1, which kind of sound like OSK0 and OSK1. And I'll show you what the keys are, but they're basically two 32-bit cryptographic keys that are used by Apple to prevent booting on non-Mac hardware. And if you're using VMware or some other VM products that let you actually run OS X, they will actually have to implement an SMC with these two keys, which I'm not sure is entirely legal, because we'll see the keys actually are copyrighted. The keys, as you'll see, are actually ASCII strings. They're actually English cryptographic keys. And maybe you can figure out that why. And we'll dump them after. I have all this on my Mac, so I don't want to switch back and forth the output. Now, back at No Such Con, I identified two other interesting keys. one of which is called KPPW and one which is called KPST. And if KPST was set, which I assume stood for kernel protection status, there were some keys that I can now access. All the keys that had the attribute private in them in that leaked Mac document, as well as in the IDB whenever flag 2 was set, which means private. I think it's 2. Let's go back and check. Private is 1. So anything that in the table had 1 set, and I don't know if I have an example. Yep, there we go. So for example, these keys over here have value 1 set in them, which means they're private. And when I was trying to read and write from these keys, I wasn't able to do that. But what happened is as soon as I saw that the code checked if KPST was set. And if KPST was set, then you could access those keys. So it lets you access the private keys. It also changes something called the memory access cycle command. And we'll see what that is. So KPPW was the code that I back-referenced would set KPST. So you had to set a specific key in KPPW, which I assumed meant kernel private password, and then KPST was set. And when I reverse engineered what the kernel password was, it was a Harry Potter spell. Specialis Revelio, which doesn't mean anything else in any other language but Harry Potter. So it's like, it could have been a Harry Potter. No, it was a Harry Potter spell, which I thought was pretty ridiculous. It no longer is a Harry Potter spell. Maybe J.K. Rowling found out and tried to sue Apple, but it's no longer that spell. But the new chip still has a KPST, still has a KPPW command. Now, what's interesting in the new chip is that not only does KPST let you access the private keys that are in the key table, but it shows and reveals a secondary key table. So there's actually some additional keys, which I've called the private keys, which are actually not even readable, not even enumeratable if you don't have KPST set, including the OSK keys, something called Mojo, and a few other keys that I'm not sure what. Some of them kind of flashing. So to even be able to know that these keys exist, you have to have KPST on, or of course you could reverse engineer the firmware and see them for yourself. So obviously I wanted to be able to set KPST again, but it wasn't a Harry Potter spell anymore. So thanks to Hexrays, I could see, okay, what's the new key? Because back in 2011, all I had to do was open up SMC handle KPPW, and it was a very clear string compare between your input and Specialis Revelio. So like, okay, let's open this up and see what it looks like. And this is what it looks like in a new chip. Basically, it compares if every byte in your input, which I called output here just because mostly it's usually an output, but it should be input here, if it's equal to G KPPW. So somewhere it stores what the expected key is, and then it checks if the key you gave it is matching the expected key. And we can see the key should be 32 bytes. And if you have the right key, KPST gets set to 1. So like, cool, let's go see what GPPW is. Except it turns out GPPW is in the RAM segment. So it's not something you can dump from the actual ROM. So, okay, so now I have to dump what's in RAM and figure out a way to do that to see what the password actually is on the new chips. So there's a few ways to do that. So one of the things I thought of doing was to use the memory access, the memory address cycle. If you go and read that old leaked document, it says there's 3 keys that let you actually read from the SMC. MACA, which you can configure what address to read from. MACM, to configure the mode if you want automatic addressing, so that every time you read from MACA, it increments MACA by 4. And MACR, which reads 32 bytes from MACA. So every time you read MACR, it reads from MACA. And if MACM is set, MACA increments automatically. But the document from Apple said this is restricted to the EPM range, only to the region that has the voltage information, not to the code, not to the RAM. You can't get to it. But there is a check there for the kernel status, for the KPPST. And the code on a new chip basically says, if you're trying to read a MACA address that is not in this range from A800 to basically B800 where the EV is, we're going to return not readable unless kernel password status is set, kernel private status is set. And if kernel password status is set, then you're also allowed to read the region at 20 million for up to 32 kilobytes, which is RAM. But this is a little bit of a chicken and egg problem because it basically says you can read RAM if you know the password, and the password is in RAM. So still can't read the ROM, even if kernel password is set, and to actually read the RAM, I need the kernel password. So then the next steps were, okay, how can we get access to the RAM? Well, we know we can flash the thing, and we know we also know something places in the RAM. So one choice is, let's reverse engineer the ROM and see how does it put it there in RAM. There's probably some algorithm that generates that key and stores it at that location. It's probably obfuscated, it's probably heavily hidden, but we can reverse engineer and find it out. We could also just be lazier than that and flash a custom ROM. Since we do have the ability to flash, I can just flash a modified ROM that dumps RAM, and I can have a ROM that dumps its own key out. Or we could be really lame and assume that Apple did not use any sort of obfuscation, and they're not actually generating a key, but the key's actually stored plain text in the ROM, and they're just copying in the RAM. And so since I'm lame, I said, okay, let's just try that out. And I just used the strings tool to basically dump all the strings in the ROM file. And let me put my key in, I'll zoom in. So this is my first attempt. Let's just see what the keys might be. So I asked it to dump all keys over. Let me change the font because my DPI is crazy. Oh, it's pretty high. All right, we'll just use the zoom then. There. So those are all the keys, all the strings greater than 32 bytes. So there's this like random bit of ASCII here. Then there's 0, 1, 2, 3, 4, 5, 6. There's add, and then there's SMC, the place to be, definitely. I'll let you guess what the key is. So like, all right, that was easy. Now let's try to actually flash some code, because getting the key out is fun, and we can dump all these keys, but I want to put some code in here. I want to, pretend I'm at the NSA, and I want to see how would someone implant something on my device. Is it really as easy to flash as it is? Because everyone claimed it is, but no one actually demonstrated, yes, you can flash this thing. So what's an SMC update? So when you get an Apple SMC update, you basically get a package, a bundle, that has an SMC flasher.efi. And then essentially reboots into EFI mode with this SMC flasher.efi, which uses Apple SMC.efi, which is a EFI protocol that's in all the Apple EFI BIOSes, and then basically flashes your SMC. So when you install that, Apple Dimage basically uses Bless, which is how you can boot into different EFI application, stores the actual SMC payload in NVRAM, runs the flasher, and then the flasher reads from NVRAM and updates the flash. Now, SMC flasher today is just basically a single tool with no input, no output, no strings inside of it. Basically tries really hard to obfuscate what it's doing. That just flashes the SMC. But the older updates, their SMC flasher.efi actually had a whole command line interface. And you could actually basically interact with it. And what it turns out is that SMC flasher was actually SMC util, which is an internal tool that everyone on the internet is trying to find. It was actually being shipped as a renamed tool in the binaries. And it still works just fine today. And you can use that SMC util to actually patch, read the keys, write the keys, and flash. So to flash something custom, you can use a new SMC flasher if you want to. But I like to use SMC util because it works just as well and actually have an input and output command line. So what does the actual flash payload look like? Well, it's a bizarre compressed payload, which is ASCII, so it looks kind of like Motorola hex or SREC. It has basically a checksum for each ASCII string, but then it contains checksums of checksums and checksums of checksums of checksums. So it's a little bit of an interesting format, but I wrote my own tool to basically dump this kind of file format into a binary file, and also to go from a binary file into this format. And this weekend, I've already created the GitHub address. I'll have it on the reference at the end. ionescu007/SMC tool. I wrote a tool that basically takes an SMC update and gives you a binary file you can load into IDA, and takes a binary file and converts it into an SMC update. Basically, for the curious, that's essentially what it looks like. The very beginning, you've got the header sums, And each header sum describes the checksum of all the checksums in a data block, and a data block describes the actual data line, and at the very end of the data line, there's a checksum for the data line. So all the checksums of the data line create a header sum, and then all the header sums, all the h's here, I've only got 4, but there's a lot more, add up to a security sum. So the security sum has to match the checksums of all the header sums. The header sums have to match the checksum of all the data sums. So theoretically, it shouldn't be too hard to basically construct your own payload. And I wrote a tool to do exactly that. So basically, I took IDA, took my bin file, and patched a simple routine, a simple address. Now, unfortunately, IDA's assemble code doesn't actually work on ARM. It says this is not supported on this processor module. So Igor, please make that work. So you can only patch it with bytes or words. So I took a simple byte, patched it, converted from bin back to SMC with the tool that I wrote, and then used SMC util to flash my new payload. And it flashed it, no errors, and then it failed. And my chip was stuck in updater mode. The fans are on at max. The battery stopped working. My backlight stopped working. Basically, my SMC was dead. Not totally dead, because it was stuck in the updater flash, since I had only broken the code, but it refused to update to load the code. So I said, OK, everyone was lying all along. You can't really flash this thing. I mean, you can, but then it will refuse to load your code. They must have code signing. It must have something in it. Well, as we saw on the memory map slide, every region of the code, the reseg vectors, the boot flasher, the update flasher, and the app flasher, all have these magic values. And when you read the ROM code, you'll see the magic values are computed, checked, and exposed to these keys. So there's these 4 keys that exist in the code: CRC-A, CRC-B, CRC-U, CRC-R. And A is the expected, the checksum it wants to see for the app code. B is the checksum it wants to see for the boot code. U is the checksum it wants to see for the update code. And R is the checksum it wants to see for the reset code. And then take those A, B, U, Rs and put them in lowercase. And that tells you what the actual checksum that it computed is. So the first thing I did was, OK, so it's telling me what checksum it wants and what checksum it computed. Let me just update my binary file with the checksums, and then it'll flash. But I also wanted to know, what are these checksums? Because they say CRC, but they're not actually CRC. Like, I've tried every CRC 16, 32. They're not actually CRC sums. So I went ahead and reverse engineered the protocol, the algorithm. And the algorithm is fairly simple, but you instantly notice that it does a maximum with 552 and a modulus 65521, which is like, these are the well-known magic numbers for implementing Adler32, which is an old checksumming algorithm that's actually still used in many things today, including the zip format. So it was basically just Adler32. Simple enough to compute that, and basically updated my tool to take a binary file from IDA, compute the correct Adler32 sums for the regions, write the correct Adler32 sums in the SMC file, compute the sums for the SMC file, and flash the payload successfully. So let's actually see if that works and do a demo. So I'm going to switch to my laptop now, show you a little bit my Mac laptop, show you some of the keys, and also show you how we actually can flash this thing. I'm not sure the flash is going to work since it's in EFI mode, but I do have a video saved of it as well. So let's unplug this. So let's just play the video then. So now it's going to unfuzz in a sec. There we go. So this is an EFI shell running SMT util, which is the old updater, which basically, if you run an EFI, shows you all these commands for reading, writing keys, and flashing as well. And the first thing we're doing here is dumping a key called BEMB. Not actually sure what this key means, but this key is interesting because it actually has the value in the ROM. So it's not a key that's generated at runtime. It's a key that's read directly from the ROM. And in the ROM and all the Apple updates, it's always 1. So whatever that means, that's what it's set to. What I'm doing next is flashing a version of the Apple update with BEMB set to 0. So this is flashing it. And once the flash was completed, we basically dumped BEMB again, and BEMB was now 0. So that proves that we can update a value inside the ROM, and it still accepts it. The next thing I did was set MACA, which is the address to actually read from, let's make full screen. So MACA is how you can actually read from the chip. If you have the kernel password, you can read the RAM. If you don't, you can only read the EV. You can never read the ROM, though. So here I've set MACA to 000. So I'm attempting to read from the reset vector. So MACA lets you select the address, and then with MACA, I can try reading this. And I'm now trying to read MACA. And what happened when I tried to read MACA is that it told me error 85, which is basically access denied. So I set MACA to 0, told it to read from the reset vector, and it refuses to do that because it's not designed to do that. So the last thing I did was flash another version of the binary. This version of the binary has replaced the if check with an unconditional jump. So this will jump. This should allow me to dump anything I want. So basically, I've modified the actual file in IDA to let me dump whatever I want. So now I set MACA to 0 again. And now I try to read from MACA. And there's the data coming out from MACA. So this used to fail. Whoops. Just reset itself. Let's go back for 1 sec. So MACA used to fail, but now it works. And the reason it works, I can show you in IDA, it's basically patched code that directly jumps to the code to dump the code instead of making the check. In other words, going back to the MACA slide here, where I had the actual C code for this, what it's basically doing is taking this if and just making it into, so that's a branch if equal, branch not equals. So this is making it a branch directly into the else. So it's a simple one-line change in the IDA file, and then you can dump any region of the chip you want. So with that, I basically created, added that to the tool, and was able to make it dump the entire SMC. Now, what's nice about being able to dump the entire SMC is that the Apple updates only have the application code. They don't have the boot code and the flash code, because they almost never want to update that unless there's something wrong. So with this code that I updated, that I flashed onto it, I was able to get the whole reset vectors, the boot ROM, the flash ROM, and the update ROM as well. So basically the whole 256 kilobytes of the chip, plus all of RAM as well, to see what was stored in there. And that's where I started doing my most of my analysis. So this chip, now that you can program it, also can talk to this driver, which is the Apple Kext. The Apple SMC Kext basically receives the interest from the SMC, receives the notifications from the SMC, and it implements a user mode I/O client that you can talk to the SMC from user mode. So if you're root, you can write to any key, and if you're non-root, you can read from most of the keys as well. The Kext is also responsible for responding to those interrupts, like your hard drive being dropped, your light sensor changing, and it can also in the new version of the SMC, respond to log commands. So I don't have a video of that. After this, I'm going to try the output one more time. But with the new SMC, you can actually write into the kernel printf log from the SMC. So I was actually able to flash a little bit of code while experimenting that actually printfs. And instead of printfing in some weird debug log that I need to have a hardware programmer to access, it actually printf into the root kernel console. So basically, from the SMC chip, I can reach out all the way to the driver and have the driver printf something, which is obviously really useful for debugging. So there's this key called LDLG, and it shows you how to do that actually. I have a few sample strings that you can use to dump things on the kernel command line. So now we can actually have our implant or our custom code even talk to the OS. There's also some properties that it uses. There's some callbacks that it uses. So the kex registers for a bunch of notifications to send to the SMC. There's some things the SMC actually doesn't know about, so the kex has to tell it. There's other things that the OS doesn't know about, so the SMC has to tell it. So basically, this code is available on the internet. Other people have written already for getting fan information. But you basically call io service get matching service to connect to the SMC. And then you get this method, user client open or user client close. And then you send handle YPC event. And then with this, you can read keys, you can write keys, you can get the key count, get the key from index, get the key information. You can read results. So you can basically, without using that EFI tool, at runtime, actually read and write keys from the SMC. Although the driver won't let you flash the SMC at runtime, you can get information from it. So the tool that I wrote, SMC tool, will also let you read and write the different keys. In the new Apple SMC, there's also some Cisco tools you can set. One of them is called debug.applesmc.debug level. The other one's called .debug path. And with this, you can get the Apple SMC driver to basically print out to the console anytime there's an SMC interrupt, anytime someone reads an SMC key, anytime someone writes an SMC key. So you can basically use it either as profiling to make sure people are not setting weird keys, or you can just use it to see when certain keys are being read or when certain keys are being written. You can also see all the errors that the SMC returns. The SMC basically has some undocumented error codes, but they have a function in the kex which printfs them. And so there's a translation table that you can read there that basically tells you what all the errors that come from the SMC are. So basically, at the end of all this, I realized that the SMC's a treasure trove of interesting mechanisms on the Mac. With the SMC kex, you have access to a bunch of interesting things. And most interestingly, anyone can flash the SMC. And the SMC now is not just bizarre Renesas SH4 code anymore that if you know like 8-bit assembly. It's simple ARM Cortex M4 code. It can talk to the OS now. It can put it on a serial log. You can use hex-race to CC code. You can compile it natively. And with a tool that I've written, you can actually flash it on the SMC chip. So basically now lets you create simple, it lets anyone essentially be able to create simple code that runs on the Mac and does nefarious things. So my interest here was to basically create a tool that lets you dump your SMC, verify the checksums, and set up a website where people can upload their checksums and compare it. Is this the checksum that your SMC is supposed to have? Because if you get all the SMC updates from Apple, then you're guaranteed that hopefully, that the SMC update you got from Apple doesn't have any malicious code in it. But some computers actually come fresh from the factory with an SMC already programmed, and there's no update for them. Like the brand new iMacs that came out last week, there's no SMC update for them. It didn't ship with a buggy SMC. At some point, maybe Apple will release an update. The Mac Minis from last year actually still have the original SMC. And the way this attack works is you take an SMC update, you patch it, and then you flash the patched update, and then you can dump the SMC. But what if you don't already have an update? So that's why I'm trying to make the tool essentially be able to take your current SMC and dump it without having to patch an existing update. And the way it's basically going to do that is it's going to flash just these very small region of SMC code somewhere where hopefully your SMC should not be using it in application code. So the nice thing about the flasher is you can decide with the protocol what to flash. So you don't have to flash the whole SMC. You can flash a micro SMC. And the job of that micro SMC would basically be to chip break itself, to jailbreak the SMC, to enable dumping of the SMC. And once that enabling is done, then you could use SMC tool, which is the tool I wrote, to dump the SMC and validate it. Because if there is no official update available, if your SMC came owned from the factory, you literally have no way of verifying this. If there is an update from Apple, then you can just get the update, compare the update with what you have, and then you know, okay, something's weird, I can just reflash the update. But if it's a brand new machine without any updates, then you're basically screwed. You just kind of have to assume that. So I'm going to release a tool this weekend which does everything but automatically jailbreak a brand new SMC. So it can convert back and forth. It can dump one that's already been chip broken or jailbroken. You can use it with IDA to create your own basic patch, but it won't yet automatically patch an existing SMC. Still working on that. My hope is to get that done and then basically be able to dump even undumpable SMCs, the ones that don't have a publicly official flash update. And then using the CRC keys, we can all compare and see, do we all have the CRCs that we expect? And I strongly recommend if you ever do forensics or you're afraid that there's some really advanced attacker going after you, you may want to check your CRC keys to make sure they're the ones that other people have the same laptop and the same SMC update as you have. And then, of course, flashing the official update is useful because then you can get rid of whatever implant was installed on your machine. But it would be interesting to dump the implant to actually see, hey, what did they put in there? I'm not saying anyone's creating SMC implants, but if they did, it would be fairly hard to figure it out today. So that's kind of my goal for this year. Use Capstone and automatically make the code self-jailbreak, so to speak. So I'm just going to try one last thing, just to try the VGA. On the slides, you're going to have a references to basically all the tools, all the evals kit and everything, and I'm sure Hugo will make the slides available. So let's try this one last time, just to show you a few things for the next 2 minutes that I've got. Yay. There we go. All right, so I'll just show you one quick thing. So this is basically the kernel log, dmesg, nothing interesting in there right now. And I'm going to write to an SMC key the value 1 to LDLG. So LDLG is a key that basically means, probably make this a lot bigger. So LDLG is a key that is the debug log, and I'm going to write 1 into the debug log. Oops, let's try 0, 1. There we go. And if I dump dmesg now, you see from Apple SMC, SMC handle interrupt event log SU699665A 55A5A 567. It's a hard-coded string that gets dumped when you write 1 into LDLG. If I write 2 into LDLG, the kernel log now says, error, no time for generic phrases. Someone's trying to be funny. And if you write 3, then it says 0, 1, 2, 3, 4, 5, so just numerate. So this is basically code in the SMC that's sending the string, and this is the Apple SMC driver responding to it. So by reverse engineering how that function works, we're able to figure out how to actually write the SMC. The other key that I mentioned is OSK, so you can also see what the OSK key is. Oops. That's the piracy key. Where did it go? Oh, God. All right. All right. There we go. So let's read the key OSK0. There we go. So that's OSK0, OSK1. For those of you who can't read ASCII, this basically says something like, "Our hard work protected, please don't steal Mac OS X." It's basically asking you not to steal Mac OS X. And some of the other keys basically let you control things like fans. So I can also, with this, turn off the fans completely. So I can write here FFFF to the key FS bang. This basically says, let me control the fans myself. I can say a new target speed for the fan is FFF. Now the fans are going to turn on like super loudly. Or I can turn off the fans. So anyway, lots of fun keys to play with that most people online know about. And just to quickly show you the tool. So this is SMT tool being ran with -I, computing the CRC sums, also telling you if the BEMBI flag is 0. So I've got my jailbroken SMC chip because I was able to set the flag to 0, which is normally to 1, and then whether or not the kernel private password has been put in. With -U, I can unlock the kernel password, and then if I dump the SMC again, now it says kernel private status equals 1, and I can dump some additional keys. So this will also put in that, that special password that lets you access things. And then if you want to create a full dump, -D lets you dump the SMC. Let's say I want to dump it to smc.dump. And because I've got my jailbroken SMC, it's actually able to dump it. If I would have done this on a normal Mac, it would not have worked because you don't have the ability to dump it. So with this tool, you'll be able to do that. Anyway, that's it for the quick little demo. Sorry for the VGA issues. And I probably have some time for some quick questions. So any questions? Yep.
The other commands that you were running, were they leaving dmessage logs too? Are there other places on the system where we could look for evidence of somebody modifying the SMC like that?
If you turn on the debug control flags that I had on a slide a few slides ago, the debug log will show you that the driver basically responded to all the commands. So if you turn on driver debugging in the Apple SMC, with these, you'll be able to see someone typing those commands. Now, someone could directly talk to the SMC and bypass the driver. And if you do that, then the driver won't output anything. But the SMC actually does have an event log on its own that I discovered a few weeks ago. Not still trying to dump it, but the SMC has an internal RAM of the last 10 keys that were sent to it as well. So there should be a way to determine that as well, but still not sure how to do that. I'll update the tool once I can figure that out.
You promised a video of a physical destruction of a Mac laptop.
I did promise the video, and my boss took it and presented it at RSA instead. So the RSA conference that CrashTry gave does have the destruction of a Mac. I do not longer have the video, unfortunately. But basically, it's very, I'm not going to do it live, but basically you take that SMC dump, and you just flash an infinite loop in the reset vector, and you're done. Because the reset vector will now not boot anything anymore, and your Mac is essentially dead. We did that with 4 laptops with a CrashTrack demo. We figured a 5th one would be going too far. So yeah, I don't have the video with me, but if RSA has made it public, so the RSA 2014 talk will show you that video. Any other questions? Nope, that's it. All right, thanks a lot. Have a good evening.